The objective of this lecture is to provide an introduction to coordinate transformations and then to apply the results of coordinate transformations to develop the 3-1-3 Euler angle sequence. So the first part of this lecture is going to be on coordinate transformations. So coordinate transformations are defined as follows. In the context of three-dimensional Euclidean space, which is what we deal with when we're dealing with mechanics and vectors, a coordinate transformation is a 3 by 3 matrix that transforms the components of a vector in one coordinate system to the components of that same vector in another coordinate system. Now, what's important about this is we're dealing with a situation where the vector doesn't change. It's the same vector in both cases. What's being changed are the components of that vector. So we have the components of that vector in one basis or one coordinate system, and we want to figure out what the components are of that same vector in yet another coordinate system. In order to do that, let's start with the following. So we can do this with a vector and then two bases. So let's suppose we say let B be a vector, which means that B lies in three-dimensional Euclidean space. And then furthermore, we have two bases here. Let E equal E1, E2, E3, and U equal U1, U2, U3 be two distinct bases for E3, which means basically that E is not equal to U. They're two distinct bases. So we could write, or we can express, so the vector B can be expressed in the bases E and U as follows. Now this is what is generally done, and what would be the way you would write this out in vector notation. If I did this, if I express the vector B in the basis E, I would get three components: B1E, and then E1 plus B2E, E2 plus B3E, E3, which is equal to B1U, U1 plus B2U, U2 plus B3U, U3. So shorthand-wise, we can actually write these as column vectors. So as a shorthand, we write the following. We say B, when expressed in the basis defined by E, this is said to be the vector B expressed in the basis E, which in this case is equal to E1, E2, E3. Similarly, we can say B expressed in U is the vector B expressed in the basis U equals U1, U2, U3. Now, because these two are column vectors, so B1 or BE and BU are called column matrices. And the terminology that's often used would be column vectors, but I want to make sure that we don't overload the notation vectors, so I'll call them column matrices in this particular case, just so, because a matrix is just generally an array of numbers, and this is an array of numbers as well, but it just happens to be an array that happens to just have three elements in a single column. So the way we would write that is we would write that in terms of a column vector as follows. We would say BE is equal to, and then it would be B1E, B2E, and B3E. And then similarly, we'd have B expressed in coordinates defined by the basis U, and that would be B1U, B2U, and B3U. Now, let's suppose that we want to find a relationship between these two column matrices. So these column matrices are of course relatable through this thing that I've defined, which is a coordinate transformation. So let's start by writing these out. So we know in general that E and U can be related through the following relationships. We could say, so we know that the bases E and U are related to one another as follows. Now I have to be a little careful when we actually relate these, but this is how it works. Is that we can say that U1 is equal to C11 E1 plus C12 E2 plus C13 E3. U2 is equal to C21 E1 plus C22 E2 plus C23 E3. And U3 is equal to C31 E1 plus C32 E2 plus C33 E3. Now we can actually figure out what these coefficients mean, because in this case these are the components of the three basis vectors U1, U2, U3, the components expressed in the basis E1, E2, E3. But if you look at these, you can actually see that there's a structured relationship between them, which is, suppose I take UI and I dot it with EJ. Well, what do I get? Well, because these are right-handed orthonormal bases, I know that if I take the dot product or the scalar product of any one of the vectors U1, U2, U3 with any one of the vectors E1, E2, E3, the only coefficient or the only component that's going to survive, because all the other ones are going to wind up becoming 0, is going to be the component Cij. Now you can see that simply by looking at one of these. Let's suppose I take U1 dotted with E2. If I take U1 dotted with E2, then I've got U1 dotted with E2 is equal to this whole first row, C11 E1 plus C12 E2 plus C13 E3, the whole thing dotted with E2. But E1 dotted with E2 is 0, and E3 dotted with E2 is also 0. E2 dotted with E2 is 1, so that just gives me C12, which is exactly the result that I have in this expression here. But you actually can see that if I take this, that the dot product between these two vectors, or the scalar product between these vectors, is also equal to the magnitude of the first vector, which is UI, times the magnitude of the second vector, which is EJ, times the cosine of the angle between these two vectors, which I'll denote as theta ij. But because these are unit vectors, because they're both bases, ui, its magnitude, is equal to 1, and ej, its magnitude, is also equal to 1. So that tells me that Cij is equal to the cosine of theta ij, where theta ij is the angle between ui and ej. So what that means is that we have this relationship through these cosines. These quantities, theta ij, and that goes I and j going from 1 to 3, are called direction cosines. And as a result of these direction cosines, we can actually assign a name to this matrix of these coefficients. So we call the matrix of these coefficients, or of the coefficients, Cij, the direction cosine matrix, because all of these are direction cosines. So this becomes the direction cosine matrix. And that relates the bases E and U in the manner shown earlier. In other words, what I mean by that is that if you go back over here, it's that in this case I'm expressing the three vectors u1, u2, u3 in terms of the three vectors e1, e2, e3. So it's in that particular order and in that particular set of operations that I'm referring to this. So we actually abbreviate this as follows. We say let C equal C11, C12, C13, C21, C22, C23, C31, C32, C33. So this is what's called a direction cosine matrix. Now it turns out that direction cosine matrices have this property that they are orthogonal matrices, and because all of these coordinate systems are right-handed, they actually have another property too. So C is an orthogonal matrix, and that actually is a very nice matrix to work with because it has a lot of really interesting properties, which means that C inverse, which is the inverse, is equal to the transpose. It also means that if you're dealing with the norm of the matrix C, it's actually equal to +1 because these bases are right-handed orthonormal, that they're orthonormal bases. So we have this nice property that the inverse is equal to the transpose because these are real matrices. Now we can use those properties to be able to start thinking about how we would actually express vectors in different coordinate systems. So we have two coordinate systems, so let's start by actually doing this. So we know that B, because we did this already, we wrote this out, we know from earlier that B expressed in the basis E is equal to B1E, B2E, and B3E. And this, of course, corresponds to the expression that we had up there originally. We had B is equal to B1E, E1, plus B2E, E2, plus B3E, E3. Now, we have a way of being able to write B also in terms of the U's. So we know that B expressed in the basis U is equal to B1U, B2U, B3U, which gives us the equivalence in terms of a vector as b is equal to b1u, u1 plus b2u, u2 plus b3u, u3. Now, let's substitute the expressions for u1, u2, u3. We have them here. There they are, u1, u2, u3. And put them into this last expression that we have and see if we can make this look a little bit different. So we have b is equal to b1 u, but then what's u1? u1 is equal to c11 e1 plus c12 e2 plus c13 e3. And then we have plus b2u. We have c21 e1 plus c22 e2 plus c23 e3. And then the last one is b3u times c31 e1 plus c32 e2 plus c33 e3. Now let's gather up all these terms and let's see what this simplifies to. So then we wind up with b equaling, well, let's gather up all the e1 terms, e2 terms, and e3 terms. So we wind up with c11 times b1u plus, we've got c21 b2u. So that's the second. That I'm looking down now on these terms, and then plus c31 b3u. That whole thing is multiplied by e1, and then we have the same thing for the other terms. We got plus. We've got, if we look down, we've got c12 b1u plus c22 b2u, and then plus c32 b3u times e2. And that just looks down, c12, c22, c32. Now let's look at the e3 terms. We've got c13, c23, and c33. So we've got plus c13 b1u plus c23 b2u plus c33 b3u times e3. Now you can see that what we've done is we've actually expressed, because we've substituted the expressions for u1, u2, u3 into the original vector expression that we had in here. We have, if you look on this page here, you'll see that we have u1, u2, u3, and we substituted in the expression. So now we have everything in terms of e1, e2, e3. Now this expression is going to equal b1e times e1 plus b2e times e2 plus b3e times e3. It has to, because I have three components here, an e1, an e2, and an e3 component. So what's sitting in the parentheses in each one of these terms has to be the component in that particular direction in the basis e1, e2, e3. So given that, I now have a way of being able to relate these to one another. So then we wind up with b1e is equal to, well, if we can write these out for starters, but eventually we want to make this more compact, because we don't want to keep writing these out in scalar form. It gets to be not only tedious, but it also gets hard to keep track of everything when you're dealing with everything as a scalar. So we'll take it one step at a time here, just to show what all this actually amounts to in terms of, what it looks like when you write it out in its full detail. So you can see that all I've done is I'm just transcribing these things to the page, to the lower part of this page here, so that you can see how they actually look individually. And so now I have these three expressions for b1e, b2e, and b3e. And you can see that they're just basically a copy of what I had above. But I can write these last three scalar equations as a single matrix equation by rearranging these quantities into, actually I forgot a term here. Sorry about this. I just want to make sure I copy all this correctly. So it's C21B2U plus C31B3U. So now I have these expressions, and what I can do is I can write this as a matrix and a column vector product. So we can actually do that as follows. We write B1E, B2E, and B3E is equal to, so now we're going to break this up into a matrix, and that matrix is going to be the matrix of these coefficients, which is going to be C11, C21, C31, and then C12, give myself a little bit more room, C12, C22, C32, and then C13, C23, C33 times this column matrix B1U, B2U, and B3U. Now, given that what's on the right is the vector b expressed in the coordinates fixed in E. You can actually see that now. This right here, which with the arrow that I've just drawn downwards, this is b expressed in the basis defined by E. And over here, what I have is I have b expressed in the basis defined by U. But in the middle, I have this matrix. I've got this matrix which I'm calling C. Now, given the fact that I'm expressing a vector in the coordinates defined by U on the right and by the coordinates defined by the basis E on the left, the matrix that is in between, that's multiplying these, has to be the matrix that transforms me from the basis U to the basis E. So I'm going to actually refer to this as the transformation, as it transforming the components of the vector from the basis U to the basis E. So T U to E is equal to C11, C21, C31, C12, and then I'll just fill these in because it's the same matrix that we had before. And this is the transformation matrix from the basis U to the basis E. Now that's the starting point for the rest of this lecture. We have that we have B expressed in the basis E is equal to the transformation from U to E times B expressed in the basis U. We can use this as the starting point for being able to develop transformations where we actually have different rotations that take us from a set of basis vectors to some other set of basis vectors. Now, the way this is done is as follows, is that in general, two bases, I call them E and U because this is what I called them, E and U are oriented different from one another in 3 dimensions. In other words, we don't just have planar transformations, but we actually have 3-dimensional representations that are 3-dimensional offsets. So if I think of this first basis as being E1, E2, E3, the second basis, which who knows what it is, it could be almost anything at this point, but it has 3 new vectors, which I'm going to call them U1, U2, and U3, And I don't know what the orientation of these three vectors u1, u2, and u3 are relative to e1, e2, e3. They could be anything. But in order to be able to make the relationship, one way to actually parameterize this offset that comes from two arbitrary bases is to use a parameterization called Euler angles. So Euler angles enable being able to parameterize the transformations, or the transformation, if you want to call it that, of the components of a vector in one coordinate system to the components of that same vector in another coordinate system. Now we can do that as follows. There are different types of Euler angles. One type of Euler angles, there's so many of these Euler angles, but one particular class of Euler angles which is frequently used, and in fact it comes up a lot in spacecraft dynamics, are what are called 3-1-3 Euler angles. So a particular variant of Euler angles is the 3-1-3 Euler angle sequence. There are 12 sets of Euler angles. We're going to look at this one. This particular set of Euler angles comes up frequently in spacecraft dynamics, and it's actually a fairly nice sequence. It has a lot of structure to it. But the way it works is that we have successive coordinate systems, or successive bases. And the way these bases work is as follows, is that we start with an initial basis. So let E equal E1, E2, E3 be an initial basis. And then what we're going to do is that successively we're going to have three different rotations, which then ultimately are going to lead to transformations. Is that rotation 1 is by an angle which will be called psi about the, I'm going to call it in quotes, 3-axis. Rotation 2 is by an angle theta about the new, I've got to be careful, the new 1-axis. And I'm going to describe what I mean by all these in just a minute. Rotation 3 is by an angle phi about the new 3-axis. Okay, so now we've started this process. Now let's see what this all means. Let's call these rotations, these 3-1-3 rotations, such that each basis that results from the rotation, I'm going to label them. I'm going to say the basis that results, or the bases. Now let's do it in 3 steps. The basis that results from the first rotation will be called, and I'm going to call it n, which is equal to n1 n2, n3. The basis that results from the second rotation will be called, and I'm going to call it Q, which is equal to Q1, Q2, Q3, and finally, the basis that results from the third rotation will be called P, which I'm going to call P1, P2, P3. So these rotations go like this. They go E to N to P, or sorry, to Q to P. That's the order of rotations. Now, okay, that's the order of rotations. Now, as we're going to see, the order of the transformations is actually the exact opposite of that. It's going to go from P to Q to N to E. This is the order of transformations. In other words, what I mean by that is that we're going to start by expressing a vector in coordinates fixed in the basis defined by P, transform to Q. Take that, transform to N, take that, and then transform to E. And we'll see how all this plays out in just a minute as we actually go through the various transformations, or various rotations, and then we'll see how this works out. So let's go through these one step at a time. And we're going to go through them in the following way. We're going to start by doing the relationship. So we're going to relate E to N, and then we're going to relate N to Q, and then we're going to relate Q to P. And these three together will form our final transformation. And then we'll collect these to obtain the final transformation. The transformation from P to E. We'll see how this works. So the first rotation. So the first rotation, remember, is by an angle. I called that angle psi, about the 3-axis. Remember, I said the 3-axis. So the 3-axis so let's see how this works. So I'm starting with a basis defined by E1, E2, and then E3, since I'm doing a rotation about E3. And then I'm going to end up with a basis that I'm calling N1, N2, N3. N1, N2, but since I'm doing the rotation about the 3 direction, N3 is equal to E3. The angle that defines this rotation is the angle psi. Now you can see that if you go back to what I did earlier, we have a way now using this. We can relate the basis N1, N2, N3 to E1, E2, E3. But more importantly, we actually can use the result from earlier to be able to then construct the transformation. So let's do this. So N1 is equal to cosine of psi times E1 plus the sine of psi times E2. N2 is equal to, well, N2 has a cosine component in the E2 direction. It has a minus sine component in the E1 direction. And then N3 is equal to E3. But now let's go back and look and see the order in which I did things earlier, because the order in which I did things earlier is really important. Remember that when we did this originally, I had written the basis vectors, goes all the way back to the beginning, the basis vectors u1, u2, u3 in terms of e1, e2, e3. And when I did that, that led me to the transformation from u to e, given the way that I had ultimately written everything. Once I finally got through all this, notice that this transformation was from u to e. So I can use that result in here, which is that if I take the coefficients or the components of n1, n2, n3 expressed in the basis e1, e2, e3, I now directly have a way of being able to compute the transformation from n to e. And the way that it works is as follows, is that the transformation from n to e follows the exact same order of operations as what I had in my earlier expressions. So Tn to e is equal to. So I'm going to read across, and then that's going to go into the first column. So what I've got is I've got cosine of psi, sine of psi, 0, and then the next entries are minus the sine of psi, cosine of psi, and 0, and then 0, 0, 1. Now, to see that this is in fact the transformation from n to e, because it might be a little confusing because of the way that everything lays out, let's do it once, and then you'll see that the pattern will repeat itself for the other two rotations, which is that n1 expressed in the basis n is just equal to 1, 0, 0. n2 expressed in the basis n is equal to 0, 1, 0. And then n3 expressed in the basis n is equal to 0, 0, 1. Of course, that makes sense because if I express any of these basis vectors n1, n2, n3 in its own basis, then those are the fundamental basis vectors. So I'm just going to get 1 in the component associated with n sub I in the ith component. I'm going to get 0 everywhere else. But now let's look and see what n1 looks like when I express it in the basis e. Well, let's look at it. It's sitting over here. n1 has 3 components when I express it in the basis e. They are cosine of psi, sine of psi, and 0. What happens when I express n2 in the basis e? I get a similar thing, except for now I'm looking at the second expression. I get minus the sine of psi, cosine of psi, and then 0. And then, of course, because n3 is equal to e3, when I express this in the basis e, I still get 0, 0, 1, which is what I got before. Notice that these 3 vectors, n1, n2, and n3, when expressed in the basis e, are given by these 3 columns, which, when I read across each one of these expressions, are the components of n1, n2, n3 in the basis e1, e2, e3, but then they're formed into a column matrix for each one of these. And you can see that these 3 vectors, n1, n2, n3, when expressed in the basis e, those 3 column matrices that arise from those expressions are the same as the 3 columns of the transformation from n to e, which makes perfect sense because if I multiply this matrix Tn to e by 1, 0, 0, I get n1 expressed in e. In other words, look, if you look, you'll see it. You'll see Tn to e multiplied by n1 expressed in n is equal to Tn to e multiplied by 1, 0, 0, which is equal to cosine of psi, sine of psi, and 0, which is n1 expressed in e, which means that had to be the transformation from n to e because I started with a vector expressed in the basis n and I transformed to the vector expressed in the basis e. So that is my first transformation. That one, we're done with that one. Now let's do the second one. So going back to the way I actually had things set up, rotation 2 is now by an angle, and I call the angle theta. So rotation 2 is by an angle theta about the new, and I'm going to put it in quotes, 1 axis. Well, what is the new 1 axis? Well, let's look at this picture from back here. When I did the first rotation, I wound up with this basis n1, n2, n3. Now I'm going to do a rotation about the axis n1. So what I'm going to do in this next picture is, in order to keep this in 2 dimensions, n1 is going to come out of the page, because that's the axis about which I'm actually doing this rotation. And if I look at the picture, I'll see that if I was to look down the direction of n1, so if I actually look down this way, is what I'm saying, then n2 will look like it's off to the right. And so it's going to look like that direction. That's going to be n2. And then n1 crossed with n2 gives me n3, which is in that direction. And the only reason I'm doing this is because I want to look down on the axis of rotation, because it's just easier to look that way, because then I can see everything in 2 dimensions rather than having to worry about seeing things in 3 dimensions. Now, I'm doing a rotation about n1, so the result is going to be a new set of basis vectors from that rotation, and the angle is theta. And because I'm not changing n1, so that means that this new basis, which I'm calling q1, these 2 new vectors are q2 and q3. And I can do the exact same thing that I did before, which is that I can relate the q basis vectors q1, q2, q3 to the basis vectors n1, n2, n3. The first one stays the same. It's just q1 is equal to n1. q2 is equal to, make sure that this is a little clearer, q2 is equal to the cosine of theta times n2 plus the sine of theta times n3. And then q3 is equal to cosine of theta times n3, and then minus the sine of theta times n2. Now, we're going to go through the exact same process that we did before, which is that before we looked across and those became the columns in our transformation. But in this case, the transformation goes from q to n. So the transformation that goes from q to n, so t q to n, is going to equal cosine of theta. Sorry, I have to be careful about this now, because the first, I have to do the first one. So q1 is going to be equal to 1, 0, 0. The second one is going to be 0, and then cosine of theta, and then sine of theta, and then 0 minus the sine of theta, and then cosine of theta. And that's because I'm preserving, in this case, the one direction, so the first column is just 1, 0, 0, which is what you would expect it to be. So this is the transformation from q to n. And again, you can go through the same argument again if you want to, just to be completely clear about how this would actually work, and it's probably worth doing it just to make sure that everything's done correctly. We know that q1 expressed in q is equal to 1, 0, 0, and we know that q2 expressed in q is equal to 0, 1, 0, and finally we know that q3 expressed in q is equal to 0, 0, 1. When we do the same thing, because we're going now from q to n, when we express q1 in terms of the basis n, we get, well, let's look at it. We get q1 is 1, 0, 0, because we're not changing that direction. q2 expressed in the basis q is equal to 0 cosine of theta, sine of theta, and then Q3 expressed in Q is equal to 0 minus the sine of theta and then cosine of theta. And of course you can see that those line up exactly with these three columns of this matrix. And so if we were to take the vector, so let's go back and see how we did this before. You see we did this exact same thing, right? In this case we're doing the transformation from Q to N. If I multiply that by Q1, and actually, we can see that when we actually did this, we've got Q1 expressed in Q. That's equal to TQ to N multiplied by 1, 0, 0. Well, this one's not the most interesting one, but that's equal to the vector 1, 0, 0, which is equal to Q1 expressed in Q. If I do the second one's probably a little bit more interesting. TQ to N times Q2 expressed in Q is equal to TQ to N times 0, 1, 0. And that is equal to, according to the transformation, 0 cosine of theta and then sine of theta, which is equal to Q2 expressed in sorry, this is N here, N. And similarly, if I take TQ to N and I multiply by Q3 expressed in Q, that's TQ to N multiplied by 0, 0, 1, which is equal to 0 minus the sine of theta cosine of theta, and then this is equal to Q3 expressed in N. And you can see that those are in fact correct, because let's look at it. Q3 expressed in N is minus sine theta N2 plus cosine theta N3, and that's exactly what we have here. Minus 0 minus sine theta and cosine theta. So that is the correct transformation. So there's our second transformation. The third transformation arises from the third rotation. So rotation 3 is by an angle, which I call phi, about the new 3 axis. So again, when I say new, it means where we left off. So where do we leave off? We left off with this basis Q1, Q2, Q3. Now what I'm going to do is we're going to look down on the direction Q3. If I look down on the direction Q3, you'll see that Q3 will come out of the page. But if I'm looking down that direction, I see that Q2 is off to the left. This is Q2. So this becomes Q3. So Q2 crossed with Q3 has to give me Q1. So Q1 is in the direction shown. And that puts me in this final basis, which is due to the rotation by the angle phi. So I'm rotating about the Q3 direction by this angle phi or phi. And these new basis vectors are P1 and then P2. And then in order to keep everything in the same order here, this is P3 and Q3. So from this last set of expressions, we actually get that P1 is equal to cosine of phi times Q1 plus the sine of phi times Q2. P2 is equal to, you've got cosine of phi times Q2 minus the sine of phi times Q1, and then P3 is equal to Q3. So from this, I can actually get the third transformation. So the transformation from P to Q is going to equal cosine of phi sine of phi 0 minus the sine of phi cosine of phi 0, 0, 0, 1. And that takes care of the third transformation. And again, we can go through the same arguments that we went through before, but it's the same order of everything. But for completeness, it's probably worth doing it, which is that we know that P1 expressed in P is equal to 1, 0, 0. P2 expressed in P is equal to 0, 1, 0. And then P3 expressed in P is equal to 0, 0, 1. But if I take P1 and I express it in Q, I get from this result here, I've got cosine of phi, sine of phi, 0. P2 expressed in Q is equal to minus the sine of phi, cosine of phi, and 0. And then finally, P3 expressed in Q is equal to 0, 0, 1. And so clearly those three line up with the three columns of this transformation from P to Q. So now we have the three transformations. So now let's look at this, and we can actually see how to transform components of a vector from the basis P to the basis E. So we want the transformation from P to E in order to transform components of a vector in the basis P to components of that same vector in the basis E. So the process actually works as follows, is that we know that a vector B expressed in the basis Q is equal to the transformation from P to Q times that same vector expressed in the basis P. Similarly, a vector expressed in the basis N is equal to the transformation from Q to N times that same vector expressed in the basis Q. And finally, we know that the vector B expressed in the basis E is equal to the transformation from N to E times that same vector expressed in the basis N. So we can actually just back substitute through this whole thing, and we wind up getting the final result, which is that if I substitute the expression for B expressed in N into the last result, and similarly if I substitute the expression for BQ into the result right before it, what do we get? Let's actually start by doing this. So we know that B expressed in E is equal to the transformation from N to E times B expressed in N, which is equal to the transformation from N to E times, but B expressed in N is the transformation from Q to N, times B expressed in Q, which is equal to the transformation from N to E times the transformation from Q to N times the transformation from P to Q times B expressed in P. So this result says that the vector B expressed in the basis E is the product of these three transformations times the vector expressed in the basis P. But also, B expressed in E is equal to the transformation from P to E times B expressed in P, which means that the transformation from P to E is equal to the transformation from N to E times the transformation from Q to N times the transformation from P to Q. And it's in that particular order, meaning that all these transformations have to be multiplied in the order in which they're actually shown here. So we start with the matrix on the rightmost, and then left multiply by the next matrix, and then left multiply by the next matrix. And it has to be in that particular order, otherwise the transformations won't be done correctly. And that becomes a 3-1-3 Euler angle sequence. And that Euler angle sequence allows us, so we've done two different things here. First, we've done the rotations to actually rotate the bases into those different configurations, starting from E going all the way to P. And then we've done the transformations, which are basically done in the opposite order, going from the vector components expressed in the basis P back to the vector components expressed in the basis E through the three transformation matrices. And this concludes the description of a 3-1-3 Euler angle sequence that allows you to be able to transform components of a vector. So this is a transformation. Let's write this down. So the result is a transformation of the components of a vector B in the basis P to the components of that same vector in the basis E. And each of these transformations is done according to the matrices that I wrote down, and then the respective diagrams that actually came with the rotations to the different orientations of the different bases, and then the resulting transformations that went along with them. So that's going to conclude this particular lecture. It basically laid down the mathematical foundation of transformations and then applied that mathematical foundation to the transformation of the components of a vector using a particular Euler angle sequence, which was called a 3-1-3 Euler angle sequence, as was defined in the lecture.